Hello everyone, thank you for this opportunity to present our work entitled Extending SDN to End Nodes Towards Heterogeneous Wireless Mobility. This work has been authored at the Telecommunications Institute in Aveiro, Portugal, and has as authors Flávio Menezes, Carlos Guimarães, Professor Rui Aguiar, and myself, Daniel Corujo. In this presentation, we will briefly address the motivation and the objectives of this work, followed by considerations about related work. We will then introduce the proposed framework and an experimental scenario for its evaluations. This scenario will allow us to showcase a range of different performance considerations, followed by conclusions and contributions. We end this presentation with indications about future work. Recent studies from Cisco have been showing the evolution trends on data traffic consumption. Specifically, it is expected that video traffic keeps on as the type of traffic that is mostly consumed, while growing substantially in the coming years. In addition to this, the shift in data traffic consumption patterns, as well as the explosion in connected devices that are able to access these contents, create very complex connectivity scenarios. As an example, more and more we see that online content are accessed and consumed by mobile devices, which are able to explore different kinds of wireless and mobile access technologies, such as Wi-Fi and 4G. In fact, last year, a greater consumption of data traffic by mobile devices was registered in comparison with the consumption done by wired devices. In 2019, it is expected that 80% of the traffic is done through mobile devices. With this data consumption explosion and devices featuring different kinds of access interfaces, new technologies are starting to be considered, such as software-defined networking. This principle, which already goes on for quite some time and is getting a lot of traction because of the upcoming 5G architecture and the provisioning of virtualization services, is a mechanism that very simply allows a separation between the control and data planes. An entity, called the controller, is able to control data flows in network entities via a protocol such as OpenFlow. This controller is then able to interface and be interfaced by other entities through northbound and westbound interfaces, allowing high-level mechanisms to impact how flows traverse a network. However, software-defined networking has been mostly targeting wired scenarios, with data control in network switches supporting OpenFlow. SDN has been considered for wireless in the past, but only at the access point or in the network access part of mobile network architectures, while never allowing the control to reach the mobile nodes. So, which could be the contributions provided by software-defined networking mechanisms in this kind of new scenario? Moreover, there is also the issue of handling multiple different access technologies, each with its own specificities in terms of control and interfacing. This aspect has been being addressed in IEEE by exploring media-independent abstraction mechanisms in the IEEE 802.21 standard. However, this standard offered its own control protocol and did not follow SDN principles. These principles, however, are at the core of an upcoming new IEEE standard dealing with access technology abstraction, which is IEEE 802.1cf, also known as OmniRun, but it is still under development. Different works in the past have been integrating SDN into wireless and even the mobile terminal, but only at conceptual level. There are experimental results available, but they only focus on using SDN to trigger specific access technology mechanisms in the terminal and thus are not transposable into multi-technology environments. So, in our work, we want to present an architecture that allows SDN mechanisms to be interpreted all the way to the mobile terminal, allowing controlling entities in the network to optimize data flows in the terminal, besides the network entities towards it. We also aim to achieve this in an access technology independent way. In the figure, we present the implemented framework where we can see how we extend the regular OpenFlow control path operation from the infrastructure and into the mobile terminals. In order to achieve this, All involved nodes, including the mobile end nodes, have an OpenFlow agent installed. In our implementation, the mobile node is a dual interface device. Also, for our experiments, we have even considered the case where the mobile node goes beyond the regular role of data consumer, but also becomes a mobile content producer. A possible scenario can be a news reporter recording some news piece in a live event by using the multimedia features of its own mobile device or smartphone towards the news station. In this way, the correspondent node, or CN in the figure, would act as the receiver in the news station. Also, in this case, the mobile node is a dual interfaced content source, and our framework allows the connectivity flow to use either the Wi-Fi or mobile network link, depending on the network conditions, allowing for an optimization of information transmission in the best way possible. In order to allow this mechanism to experimentally be validated, the mobile node has two Open vSwitch bridges instantiated in it, one per interface. These bridges are connected through a patch port, which not only allows the mobile node to be controlled by the controller entity in the network, but also allows data flows to be redirected between interfaces. The POX controller was used, supported by a script developed to handle mobility handover requests. However, our design is able to operate independently of the type of control used. In the other entities, Open vSwitch was also instanced, allowing the controller to have an overall vision of the network topology. This can be useful to provide information to trigger handovers, such as signal noise ratio or node usage in cells. We have experimentally validated two different cases which only differ in who triggers the network controller about an handover opportunity. Specifically, we have experimented a case A where the content source, which is the mobile node, is the entity that triggers the controller via an OpenFlow packet-in message. The other scenario, dubbed case B, is the listener, in this case the correspondent node, who triggers the controller about a potential handover opportunity. In both cases, the handover command reaches the mobile node and preconfigures the data forwarding to be done in the alternate network interface. A second handover command is sent to activate this preconfiguration, providing a make before break handover. Also, since this is an experimental mechanism, a kernel override for packet processing in the network stack was necessary. In both cases, with the mobile node being the data source, when it sends data, the TCP/IP in the operating system kernel is coupled to the primary network interface. The Open vSwitch can't do anything about it, but intercepts the packet before it reaches the network interface card. Once in the Open vSwitch, we were able to alter the source and destination MAC addresses to allow for a transparent handover once the new forwarding rules became active. In our experimental scenario, the mobile node transmits data via access point 1 and, at around 25 seconds of the experiment, it begins to experience a reduced signal strength due to mobility, resulting in packet loss. By using our framework in case A, the mobile node detects that the network conditions are deteriorating and warns the network controller by sending it a packet-in OpenFlow message, which triggers the handover process, with the network controlling configuring the mobile node to shift ongoing flows to the secondary interface by using two OpenFlow modifications messages. When considering case B, our framework has the correspondent node detecting that it is not receiving packets in a correct or optimal way and adverts the network controller via an OpenFlow packet-in, which triggers the handover in a similar way to case A. In case A, we had an handover delay of around 185 milliseconds, and for case B, we had a delay of 220 milliseconds in our experimental tests. We have also analyzed the impact of using OpenFlow rules for flow handover in respect to scalability by emulating different amounts of rules existing in the controller and the mobile node, and assuming that entity delay to software-defined networking procedures. We can see that there is a major increase in flow activation time for the controller when the number of emulated rules is changed from 1000 rules to 10,000 rules. Also, it is necessary to take into consideration that the flow activation time accounts for the delay between the reception of the first and second OpenFlow commands sent by the network controller towards the mobile node. Additionally, due to the necessity of having two instantiated Open vSwitches entities at the mobile node, we also verify a delay of approximately 200 milliseconds for the mobile node. These results already express some considerations and concerns that need to be handled for potential future commercial deployments of this mechanism. This aspect is further highlighted by the fact that both Open vSwitch and OpenFlow haven't been designed with this kind of scenarios in mind, which result in handover delays that can surpass the ones obtained by IP mobility management protocols. The handover process requires the use of 5 handover messages with an approximate total size of 600 bytes. Specifically in case B, we are able to distribute that value and remove some of the load from the mobile node. The greatest load, which must be reduced in future installments of this mechanism, is caused by keep alive messages exchanged by the Open vSwitch instantiated at the mobile node and the network controller. By default, these messages are exchanged every 5 seconds, causing around 3 kilobytes of overhead in a 60 seconds experiment. That does not require the addition of other signaling protocols and operates in an access technology agnostic way. The fact that it is a first experimental study of this kind of scenarios also provides a series of guidelines for the future and more optimized implementations. As future work, besides improving handover delay and how to better integrate Open vSwitch in the mobile node, we are currently assessing a comparison between these mechanisms and existing implementation of Proxy Mobile IP using an in-house implementation of that protocol. This concludes our presentation. I would like to once again thank for the opportunity to present our work, and these are our contacts. We are happy to answer any questions or provide any information that you require. Thank you and have a very nice day.